All right. What I'm going to do today is I'll finish chapter 23 and we'll start chapter 24. And I'm sure you've not forgotten your favorite part of this entire course up to this point is the derivation of all these different shapes, right? We had the electric field due to a charged rod. We had that one. If we had the test charge here, trying to measure the electric field there. We did this with a same rod. We did it with an infinitely line charge, but this time being up above here. We did the charge rod, we did it from the end, we did it from being above. We did the circular ring of charge right there. And then we did the infinite sheet of charge. And I just gave you the equation right there. Let's see if I... All right. Oh, okay, we're good. And we're going to finish this chapter. I'm going to do the last two problems real quick for you. At least we'll see how quick it takes. And then we're going to go into chapter 24. And chapter 24 is amazing. Those of you who've had calculus, you remember when you would take a derivative, you use L'Hopital's rule, you'd set up a limit, and then all of a sudden they showed you, hey, this magic little trick of dealing with derivatives, right? Yeah, why did they tell us that in the first place? I agree. I was wondering that as well too, but I think mathematicians are just interesting people. I wish I was one. All right. Both a mathematician and an interesting person. We're going to look at Gauss's law next. And Gauss's law takes care of all this junk. It makes it really easy. All right. Now it'll be chapter 24. So before we get there, I got a couple problems. So I have problems 23, 26. This comes out of the book. So 3-point charges lie along a circle of radius r at angles 30, 150, 270 as shown. Now I didn't put it on here, but I'll put it on the chalkboard for you. We want to find a symbolic expiration 4. You can see I'm not very good at typing. Just notice that. 4. All right. For the resultant electric field at the center of the circle. So I got to draw my circle here. There. And what we've got is our circle. We have a different color chalk. You see the blue up there? I can't read your mind. Remember that.
You can't really see it.
So we have a blue, we have a +2 charge there, or +1 charge here, there. We have another plus charge right there. And then what we have down here, this is a -2 charge. Okay. That's 30 degrees. That's 150 degrees. All right. And then we've got one down here at 270. At 270. All right. All right. Okay. Now, if we draw in the electric fields for these, okay, I'm going to use see if you folks can see if you can see the green, okay? So what we've got now, because this is negative and this is positive, these are going to be attracted to this, okay? So coming off of this, we've got an electric field there. All right, got electric field there. And then, all right. All right. Then we've also got an electric field there. Okay. So far, so good. You see that? Can you see the image good?
Kind of. Mm-hmm.
And then call that one E1. All right. Now what we want to do, and you can see this a little bit better in your textbook, is you want to find a symbolic expression for the resultant electric field at the center of the circle. All right. So those are going to be our vectors. That's what we've got. So if we look at the electric field, what we're going to do is we're going to break these up into I and J's. All right, we're going to break these up into I and J's is what we want to do. And we can write this now as equal to the electric field cosine 30 degrees, all right, minus the electric field cosine of 30 degrees I. So look at the cosine. We're trying to get the x component of those two right there. Now, if you notice, they're going to cancel out. I shouldn't even have to have written this up, but they're going to cancel out. The horizontal component of this vector is going to be equal in magnitude to the horizontal component of that vector, but in opposite direction. Reason being is this is off by 30, or this is 30 degrees, and this is really 30 degrees. And so this angle, I know I didn't, I'll see if I can draw a little bit better. That's not even close either. There we go. So those are going to be equal to 0. They're going to cancel themselves out. All right, so that's going to be equal to 0. This all goes to 0. All right. Now, because these, now if we're going to look at the y components of them, they're all going to be below the x-axis. So they're all going to be negative. So this becomes minus E1 plus 2E sine 30 degrees J. So that's going to take care of those two. Now we got to deal with this last one. Minus E1 plus 2E, the reason 2E because we have twice the charge there, sine 30 degrees.
So over there to the right, is that minus E to the right?
Can't hear you.
Can you hear me? Hello? 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 Hello?
Yep. Yep.
Hello. Okay. Over there to like the right, is that minus E plus 2E sine 30? Thank you.
Yep, sorry. Isn't this just wonderful, taking classes this way?
Yeah.
Wonderful.
Are you in class right now? Are you in class right now?
Yeah, I used to teach in my basement, and then I have a whiteboard. I had a whiteboard in my basement, but I took it down. So I think I'd have to teach down there anymore. And you guys don't want to hear the kids screaming when I'm just kidding. I'm teasing you. Because they're all home now. All right. Were you eating breakfast?
Oh yeah, I'm eating. I'm always eating. You know that.
Should have brought in some brownies and I'm just kidding. All right. So looking at these two, all right, looking at these two, the two vectors there, all right, and these is going to be J. All right. Now, this goes to zero because they're going to cancel themselves out. So we get to simplify this to an extent, right? So we have two of them, right? So now this equation, since we have two of them, this becomes minus 2e minus 2e sine of 30 degrees J. All right. Now this E1 up here, this E1 is actually equal to 2e simply because we have the minus 2q charge down. Leave that. We don't need to worry about that. All right. So far, so good. Now we can pull a 2e out, pull a negative 2e out. 2e times this becomes now 1 plus sine of 30 degrees J. All right. Now recall that E is equal to KQ upon R squared. We can substitute that in for here. And now we have a minus 2 KQ upon R squared times 1 plus sine of 30 degrees J. This quantity is equal to 1.5. So if you took the sine of 30, which is going to be 0.5, add 1, get 1.5. Therefore, the magnitude and direction of this electric field for this problem is going to be equal to, it becomes a minus 3 KQ on R squared. Okay. All right. A proton is projected in the direction, in the positive x direction, into a region of uniform electric field E. So here the electric field is going to be a minus 6 times 10 to the 5th I Newton per Coulomb at t equals 0. The proton travels 7 centimeters as it comes to rest. All right. Determine A, the acceleration of the proton, B, its initial speed, and C, the time interval over which the proton comes to rest. Now, the reason I chose some of this is because this does have to deal with some of the equations from last semester. But for Alex and Olivia, I know you weren't in here last semester. We're not going to deal with a whole lot of equations from last semester. They'll take the same form, but we're not going to use a lot of them. So don't freak out. If you see these equations, you go, wait a minute, I wasn't here last semester. I understand. But I like this problem because it does show some overlap from last semester. All right. So we need to find the acceleration of the proton. We need to find its initial speed. We need to find the time interval over which the proton comes to rest. So we are going to have to use a few of the equations from last semester. So the equations we're going to use, first one is going to be a force is equal to Q upon E. All right. Now we saw this earlier this semester. We saw this last week. We saw it on Friday of last week. So Jaman, Caleb, and Stephen, I know you weren't here, but this is one of the equations we have. It really is just it's K Q upon R squared, where E is equal to KQ upon R squared, is what that is. So you would have a test, what you would do is you'd have actually, one of these would be a test charge. So we went over that on Friday when you were gone. Sorry, but that's the equation for where that comes from. It's a very simple equation. It's very simple. But from last semester, what is force equal to? Well, force is going to be equal to mass times acceleration. That's Newton's second law. All right. Based on this, we want to find, if you look at problem A, says we want to find the acceleration of the proton. Well, then our acceleration of the proton is going to be equal to the charge of the proton times the electric field divided by the mass. Now, because I know all of you are good, diligent physics students, you've memorized the mass of a proton. I did. I have it on my page right here. That's how I know it. So I don't expect you to memorize it. I'll give you those kinds of constants on any test that you have. So the mass of the accelerator, the mass of the proton is 1.673 times 10 to the negative 27 kilograms. That's going to be your mass of the proton. All right. Now, do you think the acceleration is going to be positive or negative? What do you think it should be?
Be positive, wouldn't it?
Well, if it's coming to rest, right?
So that'd be negative.
It'd be negative. That's exactly right. Thanks, Josh. It should be negative. Does that make sense? It should be negative. What did I do with this? I just actually put the negative out in front because I knew it's going to be negative, but so note the acceleration is going to be to the negative. We know it's going to come to rest, so we have a negative there. And if you don't remember the charge is equal to 1.602 times 10 to the negative 19 coulombs. So these are constants. Those are going to be constants. All right. Let's see. So Q is so this is 1.602 times 10 to the negative 19 coulombs. Our electric field is given to us, and this is going to be 6. Oops. Has up there negative. Yes. So negative 6 times 10 to the 5th newtons per coulomb is going to be our field. Sorry, there's where our negative comes into play right there. So it should be negative. And then we've got the mass. The mass is 1.673 times 10 to the negative 27 kilograms. The coulombs cancel. You get a negative 5.75 times 10 to the 13th meters per second squared. Sorry, there's where the negative comes into play from the electric field.
So does the I in the electric field have any effect then?
It just the I simply tells us the direction in which it's going. It's going in the X direction. That's all I. The only thing the I gives, remember, acceleration is a vector. So it tells us that the acceleration is going to be going in the negative I direction at this magnitude.
Okay.
A good question. Good. All right. All right, so there's the acceleration. All right. And I know you've never heard me say this before, but because they put the screen in the middle of the blackboard, I can only use a small part of the blackboard.
Tragic.
Ugh. This is why I'm losing my hair. All right. B. We want to find the initial speed. So Alex and Olivia, I apologize. This is going to be equations we talked about these last semester, so don't freak out. We want to find its initial speed. What is going to be the final speed? What's the final speed of our proton?
0.
0. That's exactly right. That's exactly right. It's going to be 0. And what we're looking for is we want to find the initial speed. That's what we want to find. That's what B says. We want to find that. And we know that this proton has traveled a distance of 7 centimeters or 0.07 meters. All right. So we know the distance. We can call this our x, right? That would be our change in x. And you all remember this amazing equation from last semester, right? Because you spent Christmas break memorizing physics equations. Remember that equation? Oh yeah, that's one of the 4, right? That's one of the 4. We know that the final velocity is going to be 0, all right? We're looking for the initial velocity squared, right? Plus twice our acceleration was a negative 5.75 times 10 to the 13th meters per second. And our displacement of this was 0.07 meters. All right. We go through and do this arithmetic, and we find out that the initial velocity is 2.84 times 10 to the 6 meters per second. Any questions up on this one? So this was an equation that we saw last semester.
So we only do I because the electric field only pulls it in the I direction. Is that correct?
Yeah, it's only in the eye. We're not worried about. So it makes it pretty easy, Josh, if this particle is only going, just going in the X direction. That's all it's going. At least that's the field. The field is sending it in that X direction.
Okay.
Some type of particle accelerator. In this case, decelerator. And because the electric field is only in the eye, it's not in any other direction. We are only concerned about the eye component of the motion of this proton. All right, lastly, the time interval over which the proton comes to rest. We could have chosen any one of the 4 equations, but chose this one. Once again, we know that V final is going to be equal to 0. We just found the initial velocity. We just found that initial velocity. And we're looking for the time. So this is 0 is equal to the initial. We just found that. That's 2.84 times 10 to the 6 meters per second. Plus, we have a negative acceleration. This is 5.75 times 10 to the 13th meters per second squared. And we're looking for now we're going to solve for our time. Go through and do this arithmetic. And the time is 4.94 times 10 to the negative 8 seconds. So a really, really long time, right? I'm being facetious, sorry. But it's pretty stinking quick. Pretty stinking quick. So far, so we're doing all right? Now, I know how memorable this was for most of you folks, how much you enjoyed going through all these different geometries, all right? Coming up with specific equations for these geometries. I know that was a highlight of your life, and you spent the last couple of nights deriving all these amazing, wonderful equations. Well, I'm going to tell you it was for naught. God has blessed us with some very, very intelligent people. I wish they all knew Christ. I don't know about Gauss. But there are people in physics and in chemistry and biology, and probably as well as in engineering as well too, that figure out very elegant solutions to complicated problems. My PhD advisor was always looking for that elegant solution. He didn't want it just to be just take a big old hammer, beat the problem to submission. He was always looking for a very elegant solution to problems. And that's what we're going to see this entire semester. There are some very, very smart people. Gauss is one of them. Faraday is one of them. But ultimately, I think the most intelligent of all these people is a gentleman named Maxwell. What we're going to do this semester, we're going to take the first 3 quarters of this semester, and we're going to distill it into 4 laws. It's going to be 4 laws. Of those 4 laws, we're going to get rid of 2 of them and keep 2 of them. What Maxwell did is he saw something completely different. He took those 4 laws and he wrote them entirely different. And we'll get into them a little bit. The math is a little bit beyond this course in that they have to deal with div, grad, and curl. And those are mathematical operations that you see at the very end of calculus. Maybe some of you have already done div, grad, and curls. But the first law of that is going to be Gauss's law. All right. And this is going to be chapter 24, Gauss's law. And this has to do with what's called the electric flux. And you're thinking, wait a minute, you mean we got another thing we got to deal with? Yes. But what this does is, remember what was hard about the last chapter is you had those different geometries, right? We had the 2 charges. We had the line of charge, whether we measured the line of charge from the end or we measured it on top. We had the ring of charge. In this case, the beautiful thing about this is we get rid of that geometry problem. The geometry problem's gone. And that really simplifies. And matter of fact, it simplifies the entire equation. It is just, I think this is, the main reason I got into science was because I wanted to understand God and have a greater appreciation and certainly for his attributes. So I think this is, the times I doubt God, and it happens, I hate to say that, it does happen. I go outside and I look at the stars and I'm just in awe of them. I go back and I think of the birth of my kids and I'm in awe of that. In the summer, I look at blades of grass and think of all the chemistry occurring in a blade of grass or on a leaf of a tree. In another month or so, I'm going to tap my maple trees for syrup. Nobody knows how that sap rises. Nobody knows how that works. Something as simple as that. And that just screams that there's a creator. And he's an intelligent, he's an elegant creator. And so there's always this elegant solution. And this is one of those elegant solutions to a very complex problem. That this world is very organized by an organized creator. And that's God, Jehovah. All right. So in the previous chapter, we calculate electric fields due to a given charge. We did this by integrating over a charge distribution that produced an electric field. All right. And that had to deal with geometry. Okay. There is an alternative method for calculating the electric field based on the inverse square behavior of the electric force between the point charges. This alternative method is called Gauss's law. Gauss's law treats the electric field lines produced from electric charge in a more quantitative manner. All right. Now, the first thing we have to do before we do this is I have to introduce a new term. That new term is going to be the electric flux. Now, to give you a heads up, in about a month or so, you're going to think, did Nidegger just crack his melon? Because this all sounds like the exact same thing. It is. We're going to introduce what's called the magnetic flux. So all the stuff you see here is going to be applied to magnetic fields. Does that make sense? The only difference is they're going to be rotated 90 degrees. That's it. All right? That's it. So everything you see here, you're going to see it again. All right? So if you really pay attention now, you really get it. When you get into the magnetic field, you go, oh, we've seen this before. I can just sort of take a nap or eat a second breakfast or something like that. I don't know. But you won't have to pay so much attention. All right. So we have to first introduce this electric flux. And this is what simplifies all of this. So consider an electric field that is uniform in both direction and magnitude. And that's what we see here. What we have is we have these arrows, what these arrows represent is they represent an electric field. The electric field is going to be equal in magnitude as well as in direction. Consider an area. So what we have an area here which is going to be perpendicular to those electric fields. So in essence, here's the perpendicular area, and this is going to be the electric field protruding or going through that particular area. All right. Recall that the magnitude of the electric field is proportional to the number of lines per unit area. Remember that I showed you this point charge plus, and I said, look at the electric field lines protruding from this plus charge. If we have twice as many fields, or if the charge is twice as much, if the charge is twice as much, we'll have twice as many fields, as if it were just plus one, right? So the field lines coming from a positive 2 charge is going to be twice as large as that from a single charge. Recall that, so I mentioned it. All right, let's push it. Another way of saying that is that we can look at that as the line density, right? Line density. In other words, the total number of lines penetrating the surface is proportional to the electric field and the area. And so the electric flux, this is the electric flux. This is phi, the Greek symbol phi. E is for electric field, is equal to the electric field times the cross-sectional area that we are determining. All right. Now, we know the electric field is going to be a vector. This is going to be a vector. And so what happens is you have the electric field dotted into the area, and you get a scalar. So this is going to be a scalar. This is the symbol for the electric flux, and this is the equation for the electric flux, all right? Now, the whole idea of this is ultimately we want to get the magnitude of the electric field. That's really what we desire, but it's not easy to do because it depended upon the geometry from the previous chapter. So I have to move you over here because I got to do a little bit of writing. Yeah, the electric flux is equal to the area, the electric field times the area. This is going to be a dot product, so that gives us a scalar. In units, for the electric flux are going to be, it's a Newton meter squared over a Coulomb. Now, I chose you a very, very, very specialized case, a very specialized case. And that in this case, what we have is we have the surface area, and that the surface area is perpendicular to the electric field. All right. What if that's not the case? What if that's not the case? Because that isn't always going to be the case. That's right. What I'm going to do is I'm going to punt and go home. Just have somebody smarter than me figure it out. But then again, that person's going to make a lot more money, and I got mouths to feed, and they eat a lot of food. So we got to figure this out, okay? We got to get this thing figured out. All right. Before I go any further, I do want to talk a little bit about conductors. I don't know why that's in there, but all right. You know, why don't we just get right to the flux? You know, why necessary? Just get right to the flux. So he said, what if that field is not perpendicular to the surface that we pick? Because that's going to be that's ultimately what's going to happen. All right, that's what's going to happen. So what if the surface is not perpendicular to the field? Well, the surface of the area can be at an angle, can be at some angle of that uniform electric field. The same number of lines cross the perpendicular portion of the surface as the surface that is angled. All right. So what do I mean by this? All right. Let's say within here, somewhere inside of here, all right, we've got a charge. There's a charge somewhere in here. All right. This charge is going to be giving out a uniform electric field. All right. Now, this is not a geometry that we're familiar with, right? We in the last chapter, we looked at some geometries that we were very familiar with, that we knew the equations for, certainly for those geometries. But we have a shape here that we don't know off the top of our head what the equation for that is. What we do now is, I told you that the area was a vector. Now, the only way that area is a vector is because I take the vector normal to that area, which is what I have here. So I have the area, this vector here represents the area, but it's going to be normal to that actual area. So the length of this vector, the magnitude of that vector is going to represent the area by this little tiny rectangle there. Does that make sense? All right. Now, the angle we're going to measure is going to be the electric field relative to that surface area vector. That's what we're going to do. That makes sense? We're going to compare that to the surface area normal.
So what's the box represent then?
This box represents some little area that we're choosing, Josh. We're gonna break this goofy shape up into a bunch of little surface areas. So this box right here represents one of those little surface areas that we've selected.
And that's what we're going to measure, like the number of lines through?
Yes, that's exactly correct.
Okay.
And what we're going to probably do, Josh, what would make a lot of sense is we're going to pick the exact same area for just one line to pass through.
Okay.
Does that make sense?
Mm-hmm.
And what we're going to do, and I'll tell you, I'm going to give you a heads up. What we're going to do is we're going to get rid of that area.
Okay.
And that's what we're going to do. We're going to get rid of that area because that was the problem. If you remember the last chapter, that geometry. Another way of saying geometry is area. If we can get rid of that, if we can figure out a way to do that mathematically, then who cares? All right. So that's ultimately what we're going to do. Okay. Now, you're right, Josh. What does this area represent? Well, it's because we're going to pick these little tiny areas and we're going to sum over all of those areas, right? We can sum over all those little areas, all right? If we do the summation, you can treat that mathematically as an integral, all right? But I don't want to get ahead of myself. The flux, the electric flux, is going to be equal to the electric field dotted times the area, that vector, right? Now, if we want to find them, that works great so long as that the angle is zero. If the angle is zero, then it's the same, or then this becomes 1. But that isn't always going to be the case. Therefore, our electric flux is going to be equal to the electric field times the area times the cosine of that angle that we have. All right. Complex surfaces, such as what we have here, can be divided up into many, many little small areas. We would actually sum over all of those areas, but you can very easily turn those sums into an integral. Very easy to turn those sums into an integral. All right. Sure. So, all right. So the integral is that of a surface integral, meaning that it must be performed or evaluated over a surface in question. The electric flux depends on both the field pattern, right? The field pattern coming off this, as well as the surface. All right. Now, in order for this to work, we need to choose a surface that is going to be closed. So a closed surface, this is a surface that divides a space into an outside as well as an inside region. So the whole idea of this closed surface is that you have an inside region and you have an outside region. So you have an inside region and you have an outside region. That's the whole idea of closed. It seems very basic. Those happen to be, in this case, they happen to be called a Gaussian surface. They happen to be called a Gaussian surface. And the reason we have this is that one cannot move from one region into another region without crossing the surface. So if I'm going to leave this room, I have to go out of that surface, that wall. The same thing happens here. A sphere is an example of a closed surface. All right. Now this slide here, the only reason this slide is here is because what we've got, let's look at this picture and then we'll look at the math. This basically gives the justification for the cosine, of theta. All right. Now here what we have is we have field lines coming through this surface, and this surface is going to be perpendicular to the field lines that are coming in. All right. So this surface is perpendicular to those field lines. But let's say we decide to take a surface, we bend it, or it comes in at an angle now. So now what we have is we have the field lines coming in at an angle. All right. Now, because this is at an angle, it's going to change the electric flux because it's now going to be going through a greater area, which is going to reduce the electric flux.
It's kind of hard to see the picture.
Can you see the picture?
Kind of washed out, it looks like.
Let me shoot some lights. Is that better?
No, it made it worse.
It made it worse.
Yeah. That's better than the first.
That's about the same, but it's a little
Yeah.
better.
How's that?
You good, Steven?
Nah, I'm chilling.
Is that better?
It's a
Or the
little
same?
better.
That's good. We'll take that. That's good. That's fine.
How's that? Is that any different?
Not really.
Good, because I shut the last window. I don't want to shut the last window. I kind of like looking outside. There's a bunch of kids having a snowball fight. I always want to quit and go out there and join them, but I'll be doing that when I get home. So the 2 hours I'm getting home. All right. So what we have here is because we tilt this at an angle, that's going to affect the electric flux. All right. So we're on slide 5, chapter 24. I should have these on Blackboard, right? So these should be on Blackboard. I checked them. I did fix that one, Josh. Thanks. I got the right.
Sir. You got it.
Done. All right. I got the thanks, Josh. I got chapter 23 on there. Thanks, Marty, that you let me know that I'm doing it right. Who knows? Anyway, what happens is because this is at an angle, that's going to affect the electric flux. Because it's coming in at an angle as opposed to coming perfectly perpendicular. All right. All right. Any questions? Does that make sense? All right. All right. So the electric flux, even if it's an open surface, the electric flux, which is what we had before, is going to be defined as the integral of the surface integral. I don't know if you folks have done them yet. We're just going to treat them as a regular integral. This is where this portion of physics starts to get really hard if you go into some of the more advanced stuff. Simply because you're going to be doing different types of integrals. All right, we're going to do a path integral, but the electric flux is defined as this. And what I want to get to today is a practical, and I always think of Jaman because he always says, is this an equation we can use? And Marty asked that, that's great. Kind of if you're given functions. But what I ultimately want to get to is that working equation, the real simplistic working equation we got. Look, the end of the snowball fight. All right.
So in its current form, the integral is not going to be very useful to us then.
Well, it is useful so long as you're given a function for this and you're integrating that function over the area.
Okay.
Does that make sense?
Mhm.
If you're given just a value, Josh, it's not that simple. Does that make sense?
Mhm.
And ultimately, I keep saying we want to get rid of this area because that's the problem. I mean, that's the huge problem is we want to get rid of that area because that's the geometry.
Mhm.
And you said, what does this square represent? Well, you want to count up all those squares. I mean, what are you going to pick for that area? That makes it very arbitrary for how you would do it, and maybe how Jonathan would do it, and how Stephen would do it, and Caleb, and Olivia, and Marty, and Bill, and everybody else in the class, including myself. So it'd be nice if we could get rid of that issue. All right. And here's just another picture. right? We have an electric field going through some kind of surface, and we're finding the flux. It's just another goofy picture saying the exact same thing. All right. All right. And of this electric flux, we have three areas we can look at. We have areas 1, we have area 2, and we can have area 3. All right. Now at area 1, what we've got is we've got the flux or the field coming out of area 1. Can you guys see this picture? Is it too washed out?
It seems like the light is just a little bit too bright on it at times, but it's all right.
Any better? All right, so on slide 7, the flux, and this is just convention, the flux coming out of the surface is going to be positive. All right. In this case, number 3, the flux coming in is going to be, let's see. Sorry. What did I do? We have 3 scenarios of a closed surface. 1, the flux coming out of the surface. Okay. The flux coming out of the surface, the flux coming out of the surface, right here.
Yeah, I can't see that.
It's where you're walking around.
No, I can see it. Never mind.
The flux coming out of the surface, if it's coming out of the surface like what we have here, is going to be positive, right? So the flux coming out of the surface, is going to be positive, right? The flux coming out of the surface is going to be positive. The flux coming into the surface is going to be negative. The flux coming into the surface, like what we have here, the flux going into the surface is going to be negative. And then lastly, what we have here, number 2, what we have is we've got, it's blown up a little bit here. You've got the surface, you've got the surface normal, the area normal, and you have the electric field being perpendicular to that normal. Now the cosine of 90 degrees is 0, and so therefore the flux in this situation is going to be 0. Right? So the flux coming out is positive, the flux going in is negative, and the flux perpendicular to the surface normal is going to be 0.
That was looking back at the EA cosine theta. Is that kind of?
Yes, that's exactly right. That's exactly right. Yep. Yep. This would be 0. This would be 180, and that would be 90. Yep.
Okay.
Yep. Exactly right. All right. The next one is a problem. Because I don't have time to do the problem, I'll do that for you on Friday. And I just want to get to where we get to this Gauss's law, the working equation of it, and I'll let you go because I got to go to a meeting. All right. So I will do the example problem slide number 8. I'll do that on Friday for you. All right. Okay. Now, look at the derivative of the electric flux. That is going to be equal to E VA cosine theta. All right. Now, if my theta is equal to 0, then this becomes E VA. All right, because cosine of 0 is going to be 1. If I integrate the derivative of the electric flux is equal to, I can pull the E outside the integral, dA. All right, now my flux, my electric flux is equal to the electric field times the area. All right. Well, what's the area? The area, if I happen to select a sphere, which is the easiest to use, is going to be 4 pi r squared. All right. If you remember correctly, E is equal to our constant K Q over R squared. Remember that? That's what the electric field is equal to. So now let's plug this together into now our electric field. Our electric field is going to be equal to E, which is K Q over R squared, times now our area is 4 pi R squared. Our R's cancel, all right? Our R's cancel. And so what we get this to be equal to now is this is now 4 pi K upon Q. So far, so good? But do you remember what K is equal to? Well, K is equal to 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. All right, so we can plug our K into this now. And our electric field now, so this is 4 pi Q all over 4 pi epsilon naught, right? 4 pi cancels. Now our electric flux is Q upon epsilon naught. All it depends upon is the charge inside that surface. We don't care about the area.
And epsilon naught, that's a constant.
That's a constant. Epsilon naught is the permittivity of free space. All it depends upon is the charge inside. So long as it is closed by that it's enclosed by a closed, oops, sorry. So long that it has a closed surface. All right.
Okay.
All right. I gotta run off to a meeting. Well, actually, it's a Zoom meeting. Zooming for 3 hours straight. I think I'm gonna have issues. Just kidding. I already have. All right. Any questions?
So that's the usable, like, working form of the equation
That's
then?
of the flux, of the
The
flux.
flux. Okay.
Of the flux. So what Gauss did is he said, okay, we have these electric fields, whoop-de-doo, great. But if I can come up with a flux, almost like a density, if you want to think of it that way, Josh, that's really what this is. This is almost like an electric field density, really. And I'm just going to pick some kind of surface, any kind of closed surface I want, i.e. probably a sphere would be the best one, right? Circle, a sphere. And if I do that, I've just simplified the entire thing. Who cares about all this goofy charge stuff, right? You know, charge rod and stick some stupid pointer. Let's just encase the whole thing with some kind of sphere.
Okay.
Does that make sense?
Mhm.
And so now we don't care about the geometry. We're gonna just pick a surface.
So then our like EA cosine theta, that's not really,
We
relevant
may
anymore then?
use that. We may use that. Yeah, we may use it to find the
Okay.
electric field.
Okay.
But for this flux thing, he just kind of, It's almost like a hand waving argument. I've always thought somewhat a little bit. But let's just throw a circle around, right? It's kind of that whole spherical cow argument.
Mhm.
But it's elegant. It takes care of all that goofy math. All right, I got to go to my meeting. I miss you folks. It's not as enjoyable talking to an empty room. So anyway, take care. Drive safe if you're driving anywhere, and please keep Nate in your prayers. His dad, I guess, is not doing well. So anyway, all right, we'll talk to
Thank
you
you,
later.
Professor. I'll see you.
Anytime you folks need anything, let me know. I have a meeting at about 11ish. I'm not going to be on campus after. I'm going to take off and go.
Boys fishing.
I don't know. I might. Thought about it.
Quick question, Mr.
Yeah.
Niger. Were the roads bad this morning or no?
I drove in about 35, 40 miles an hour. They're a little slick, but I don't have the best tires on my vehicle. But Marty, I grew up in a place where we got snow the end of October through April, and it never melted. We always drove on this stuff, and
Oh, wow.
it never melted. It would compress, but it never melted. So I go to Minnesota every year for Christmas. With the exception of this year, I either drive through an ice storm or a blizzard. So they're a little slick, but they're not terrible. I mean, as long as you take your time, you're not in a hurry, and give your plenty of time to accelerate and to brake, and you're not going to pass anybody, and you keep great distance, you should be fine. So, assuming nobody comes into your lane, I mean, that's the only thing you can't control.
Gotta slow down.
Great. Thanks,
Yeah.
Mr.
Yeah,
Niger.
but it's not. I mean, they weren't bad this morning, but they were slick. I mean, I blew through a stop sign in Concord. There were no cars there, so I didn't realize it was quite that slick. But no, but I got crappy.
Not no stop, right?
I eventually stopped, but
Yeah.
thankfully the cop wasn't parked there as he always is. So, but anyway, I
All
certainly
right,
miss you folks. It's only been one day, but I do like teaching you all. So anyway,
Miss you,
later.
Joe.
We'll see
Appreciate
you
Nate,
on
you're listening.
Friday.
Nate, if you're listening, we're praying for your dad and your mom and you guys. So hang in there. Sorry.
Have a good one.
Yeah.
See ya.
Have a good one.
Friday.
Thank you.